Welcome back. Right now, I want to talk about control systems, more so PID controllers. What are PID controllers? Why do we use them? And how do they fit into this buck converter that we're designing? Right. Before I go into the mathematics, in fact, I think I'm going to do away with the mathematics for now, and we'll revisit that. But however, I will show you control system in a way that fosters understanding rather than showing you mathematical equations. And to do that, I want to head on over to Simulink, and we'll start with a simplified system like this one. Let me remove the disturbances, constants, and all of that. And we can just close that up. Okay, delete. There we go. Right. Let's imagine for a minute that this is a plant. A plant could be the buck converter that we want to linearize. It could be a motor. It could be basically anything that you want to control that you refer to as a plant. All right. And we want to inject a voltage into this plant, a step voltage. What I mean by a step voltage is it's the equivalent of just switching on a light, for instance, or a switch, because the voltage will rise suddenly, very suddenly, from 0 to a maximum point. And that's what a step voltage is. This is how we test systems to see how they will respond to a step input or a step change in the input. Right. So if we run this and we observe the output on the scope, we will see that our desired signal tracks and follows the system input quite well. We do reach steady state at around 6 seconds and there's no overshoot, so that's good. It's tracking quite well. So if we're getting the 1 volt that we want in the output, then why do we need a control system? Because essentially all we want to get, if we input 1 volt here, we want to get 1 volt in the output. If we input 2 here, we want to get 2 out in the output. That's essentially what this does, this particular system. So why do we need a controller then? We're already getting that. What if we have a disturbance? And a disturbance in the context of a buck converter could be the load changing, the parasitic parameters changing in the design of the buck converter. Remember, we designed our buck converter to operate for a 2.5 ohm load. And when we changed the resistance, we saw a change in the voltage as well, which is undesirable. So what we're trying to do with a disturbance is we're modeling such changes, such unpredictabilities, whether it's an environmental change that's going to impact the system, or a change within the system itself. Right, so now if we introduce this disturbance in this system, let's see if we still track the reference waveform as accurately as we did before we had a disturbance. The answer is no. This is our reference, but this is our output. So the output is 0.5 volts off. That's not right. Meaning we can't really account for disturbances in the system. We can't account for inaccuracies in modeling because we have no way of looking at the output, then making changes to the input based on what we're seeing on the output. If there was some way that we could observe this output and adjust our input, or rather adjust our command signal to this plant based on this output. So another way of looking at it is if you're driving and you see that there's a stop sign right up ahead, what you do is you gradually apply the brake so that when you get to the stop sign, you bring the car to a halt. So in essence, you're acting as a controller for that car, as a speed controller to be exact, because you're observing the output, which is the speed, and you're making changes to your reference signal, this being the reference signal in this case, And that reference signal will then determine your command signal to the plant being the engine. So by looking at the output and adjusting your command signal, you can then sort of get the desired outcome. So how do we replicate this in a control system or in our buck converter? Well, I'll present to you a couple of ways of doing that. Let me just remove that and let's comment this out. Comment out. There we go. What if we had feedback? What do I mean by feedback? By feedback, I mean we take the output, we bring it back, and we subtract it from the input. We get an error, we amplify the error by some factor, and we feed it to the system. Let me just rectify this. There we go. And we feed it to the system. We keep on observing the output and we make adjustments accordingly. What would happen then? Well, let's run this and let's see if there is any difference. Right, we are tracking the signal, but there is steady state error. So why would we go for something that gives us steady state error? Why would we make our system less accurate? Why would we do that? By the way, this is called a proportional controller because all we're doing is we're multiplying, we're amplifying the error with a constant. So be it that constant is 0.1, 2, 12, 100, doesn't matter. This is called a proportional error because proportional controller because you're multiplying the error by a constant, right? Hence proportional controller. All right. Now, as I was trying to say, what if we've modeled the same disturbance that we modeled in the previous circuit? What happens then? Will we see something different? Let's see. Okay, then let's close the control loop. Make this a bit neater. There we go. And we made it 0.5 there, so let's make it 0.5 here. Now let's look at this compensated system that has a disturbance. Remember that when we had a disturbance in the uncompensated system, it went haywire. Now let's see whether this feedback system actually makes a difference. Does introducing feedback make a difference in the behavior of the system? Yes. We accurately reject all those disturbances. Yes, we still have that steady state error that we had, and I'll show you how to get rid of that in a minute. But we are rejecting disturbances a lot better now that we've got negative feedback. So we're getting better at this. Now we've learned how to reject disturbances and inherent inaccuracies in the system. All right. What if we wanted to get rid of a steady state error? What would we do then? This brings us to the all-important integral controller, or the I term in a PID. Remember that PID that you studied about in your undergrad? Yeah. This is where it becomes important. So let's uncomment that and let's bring it down a bit. Or let me go up. That, there we go. Right, so right over here is an integrator with the gain of 5. Now, before I go into the mathematics of how this works, I'm actually going to attempt to give you an intuitive explanation. When you integrate a curve, say it's a parabola, you're actually working out the area under that curve, right? It's the sum of all the small rectangles that you would fit inside that curve. If we look at this control system over here, this block diagram, we see that the output is brought back, subtracted from the input, then we get an error term. Meaning this error term is what's being integrated. So if this error term or if this error function has some sort of finite area underneath it, that is what we'll keep integrating and integrating and integrating, and we'll stop integrating it when the area underneath that error term becomes 0, because then that means we have no error. Does that make sense? Allow me to elucidate that a bit further. I'm actually going to run this, and what I'm going to do is I want to observe the error, and I want to observe the trigger signal that we give to the plot, or the driving signal, if you will. Right. So what you see in yellow over here is the error term or the error function. And over here is the signal that you're giving to the plant. Remember, the reference is 1. So when this becomes 1, it means we've reached steady state, because we're just giving 1 to the system and the system is giving us 1 back. But what I want you to look at is this part of the error over here. Let me just maximize this so that it's clearer. This yellow graph, the error term or the error function, starts out at 1, because when you just start out your control system, you've got, when you just start running your simulation, you've got no output. Your output is essentially 0. So you just have this reference at 1. So 1 minus 0 is 1. And that's why this starts out at 1 over here. And it keeps decreasing and decreasing and decreasing, and then it goes negative and it rings and does all of that. Now, I want us to look at the area underneath the yellow curve. The area underneath the yellow curve is at its highest right at the 0 crossing, because you're summing up the area from this point all the way to up there, down here rather. So the area underneath this entire portion is what you're integrating, right? So this, and if you then look at the blue curve, we are giving the highest input or the highest driving signal to the plant right at the 0 crossing, because this is where our area is at its largest. And because our area is at its largest here, we need to drive that plant as hard as we can so that we reduce this area. And this is what causes the error to go negative, because we've essentially overdriven that plant. And now it becomes negative. When it becomes negative, we're trying to then reduce the driving signal, because we're essentially reducing the area underneath the curve. So when it becomes negative, then it goes positive, negative, and so on and so forth. And you can see as it fluctuates and it rings and it does all of this, the driving signal changes as well. So another way of looking at it is that this, the blue curve, is the integral of this multiplied by a factor, that factor being the gain factor of the integral, which is 5, right? So this is how the integral controller works. It looks at the error, it integrates it, and it takes action based on the area underneath the error function. All right, let's look at the output scope. Right, like I said, we're actually, let me see if I can bring up both of them so that we have a clearer picture. There we go. All right. So our step input is the blue line over here, and our output is the yellow line that rings and does all of that. Okay. So what do we see here? We see that over here, our error was 1, obviously, and our maximum drive signal to the plant occurs at the 0 crossing. And because the error now goes negative, it essentially means we're overdriving this plant. And this is why we see an overshoot over there. And then we try to compensate because we're seeing that the area under the curve is now negative. So in order to undo that negative area, let's go positive. But we overdo it, and that's why it undershoots. And then we see that, oh, we've undershot, and the area now is positive again. It's a finite positive value. So let's try to compensate and go negative. And we overshoot, undershoot until we get to steady state. But we can see right about 10 seconds that we then start following the input signal precisely. So the integral will give you 0 steady state error for a system of this nature. I will talk about system types a bit later on. The other thing I want to discuss is the impact of the integral gain. See here, our integral gain was 5. So now let's change that to 1 and see if it has an effect on the overshoot, the undershoot, the stability, and whatnot. Right. Let's look at the output. Now we're not ringing as much, we're still overshooting. And if we look at the error still does go negative, but our overshoot has been reduced from 1.4 to about 1.19, 1.18. So if we increase the integral gain too much, then we run the risk of overshooting and ringing quite a lot, and we might even drive our system to the point of oscillating. That's something that we want to avoid, but more on that on the control systems lecture. Remember, this is more of a design course, so I will assume that you do have fundamental knowledge of control systems. So let's close these two. So we've now discovered that with the integrator, we can essentially reduce our steady state error to 0 with a